In this example, we will talk about how to analyze a circuit, RC circuit, when the input is a pulse voltage instead of step function. First of all, let's look at the circuit. In this circuit, we have one voltage source, VST, one resistor, R, and one capacitor, C. We are told the initial condition, everything is at rest, particularly Vc, t equal to 0 is equal to 0. There is no charge stored in the capacitor. And secondly, we are told that the input of the voltage is a pulse with t. This is Vst. It's a finite pulse with t. Now we would like to calculate what is the voltage of Vct as a function of time. So today we would like to give two solutions. Let's first look at solution 1. For this solution, let's first consider what will happen if the input voltage is a step function instead of a finite with pulse. By the way, this pulse height is V0. So first of all, let's consider what will happen if the input voltage is a step function with the magnitude of V0. According to what we discussed, we can first decide on the initial and the final value. The initial condition is already given, that is Vc t equal to 0 is equal to 0. And also we can decide what is the final condition, that is when t equals to infinity. When t equals to infinity, the capacitor is fully charged up. There is no further current going into the capacitor. So all of the voltage from the source is distributed across the capacitor. So Vc is equal to V0. Now we can graphically express the evolution of Vct as a function of time. So the initial state is 0, and the final state is V0. So it will go from 0 to V0. We know the physical solution is a curve like this. And from our previous discussion, we also know that this curve is proportional to 1 minus e2 minus t over tau, and tau is RC time constant. And we can easily write out the expression of Vct as 0 plus V0 1 minus e minus t over tau. Here, tau is RC time constant. Here, we are only consider the output when the input is a step function. Now, let's consider a real situation where the pulse stopped at t equal to capital T. So that is, in this output voltage at t equal to capital T, afterwards, the input is removed. So the input is 0. Let's draw the circuit if there is no input. Again, we can utilize the intuitive analysis First, let's consider what is the initial condition. The initial condition is when t equal to capital T. And from the first part, we know when t equal to capital T, the voltage is this data point. Let me use a different color. So the voltage will be this data point. And we can analytically express it, that will be V0 1 minus e2 minus t over tau, using the results that we obtained from the first step. And we can also decide what is the final state for the capacitor voltage when t equal to infinity. When t equal to infinity, the capacitor is fully discharged. There is no voltage, no current inside the circuit. So VCT equal to infinity equal to 0. And then we can, again, graphically express the solution. So here is T, here is VCT, here is V0. According to the first step, we calculated what happens between 0 and T. After T, it will no longer do this, but instead, the new initial point is this, and the final point is 0. So it should satisfy exponential relationship. It will undergo a decay like this. And we know this trend must proportional to e2 minus t over tau. But now, since the new starting point is t equal to capital T, so it's shifted, so it will be e2 minus t minus capital T divided by tau. So for this region, we can write out the expression, that is VCT equals the initial condition, which is given by this V0 1 minus e2 minus t over tau, followed by an exponential decay. And we can further simplify this as V0 e2 minus t minus capital T divided by tau minus V0 e2 minus t over tau. Summarize what we got from step 1 and step 2. We can get the final solution as when t is bigger than 0, smaller than capital T, we have VCT equals V0 1 minus e2 minus t over tau. And when t is bigger than capital T, smaller than infinity, we get VCT equals V0 e2 minus t minus capital T divided by tau minus V0 e2 minus t over tau. So this is the final solution for the circuit that we discussed when the input is a finite with pulse. So this is the first solution. In the following, let's look at a slightly different solution. To facilitate our discussion, let me draw the circuit again in this page. So this is VST RC plus minus VCT. So first of all, we notice that this is a linear circuit. And for linear circuit, we can always use superposition. For this specific problem, let's look at the input. Input is finite with powers. It's easy to say that this type of input can be represented as a superposition of two step functions. Let's call the first one is VSAT, which is given by a step function starts at t equal to 0. And then let's call our second step function as VSBT. And this step function starts at t equals capital T. You can easily say if you use the first one, subtract the second function, you will get this finite powers function. According to what we learned about superposition, we know if you can calculate the output under VSAT, which is VCAT, and then the output under VSBT, which is VCBT, then VSA minus VSB should lead to VCA minus VCB. So first of all, let's consider what is VCA. Actually, VCA is just output in response to this step function of VSA. This is what we already calculated. That is VCA equals V0 y minus e minus t over tau, which is shown here. The second question is, what is VCB? We notice that the input function VSB is just a time-shifted version of VSA. So if you simply shift in the time along the time axis toward the right by t of VSA, you will get VSB. So we know VSB equals VSA t minus t. Then, because the system is also a time invariant system, we can easily say VCB t should also equal to VCA t minus t. So we can just simply replace the t in the first expression as t minus capital T. So we can easily get the expression of VCBT should be equal to V0 y minus e minus t minus capital T divided by tau. Now we can easily subtract those two output functions, VCAT and VCBT, utilizing this linear property. So let's write it out. So by the way, we forgot one point. That is, this expression only holds when t bigger than capital T. If it's not this case, then your output should be equal to 0. Between 0 and t, capital T, the output corresponding to VSBT should be equal to 0. So when we do a superposition between those two functions, we can discuss between two different regions. First is when t is smaller than capital T, we know the output VCT is just simply VCAT plus 0, which is V0 y minus e2 minus t over tau. And when t is bigger than capital T, both VCAT and VCBT are finite. So we get VCT is equal to VCAT minus VCB. Let's write it out. It should be equal to V0 y minus e2 minus t over tau minus V0 1 minus e2 minus t minus capital T divided by tau. We can simplify this. V0 will cancel out, and you get V0 e2 minus t minus capital T divided by tau minus V0 e2 minus t over tau. So this is the solution that we obtained using a simple superposition. Now if we compare this solution with the solution that we obtained just now, which is using a slightly different method, you'll see between t, for t between 0 and capital T, it's always this expression. And for t bigger than capital T, it's this expression. So they are the same. So those two approaches are equivalent to each other.